Hello again, everybody. My name is Rain, or Pixel Rain for short, and today we're going to be going over how to smooth out our voxel terrain that we've been working on. This is probably going to be a little bit longer of a video, and next week or next video will also be pretty interesting because I plan on reworking a decent amount of the actual chunk rendering, get some more speed out of it, hopefully. Just to give you a preview of what we're going to be looking at, though, this is the terrain smoothed out. The trees are calculating from a sign depth function, or sign distance, excuse me. And the terrain and all the voxels within it are calculated using a 4x4x4 density array within the voxel, which is how we can get this smooth-ish approximation. Definitely has a low poly feel to it, but I would say that is almost exclusively due to the normals at this point. So without further ado, let's go ahead and get into making our smooth terrain. Alright, so to get started, the first thing we're going to be doing is reconfiguring our voxel data, which will be a lot more bit shifting involved than it used to be. So we'll start on voxel CS, and due to the changes, I am just going to copy and paste and then briefly run through them. Okay, so this is what our new voxel struct is going to look like. We'll have an integer voxel data and two unsigned integer density datas. For those of you who did not know, there are 32 bits in an integer or an unsigned integer. So that gives us a little bit of room to play with, and as you can see, and as you've seen in some previous videos, the only way that we can cut down on our memory usage is by utilizing that. So our voxel data now contains an ID that takes up the first 8 bits, then there's an active value that takes up the second set of 8 bits within it, and then the fun part is the actual density field. If you have some questions about bit shifting, feel free to jump into the Discord and ask me. It took me a little while to wrap my head around it, and I'm still not super great at it, but I know enough to get by. Then we have an index from coordinate function. So this is just how we get our 0 to 63 index of the density data field. It's the same thing we've been using for indexing into our voxel array or things like that. Then we'll have two functions, get voxel density and set voxel density, where we're going to get the index. If the index is greater than 32, then that means we need to be modifying density data B as our second set of density data. And all we're doing is checking if our 1 bit at our index isn't equal to 0, then it's a solid voxel. If it is equal to 0, then it's empty at that place in density. And then for set voxel density, we'll get our index and do the same thing. Index is greater than 32, subtract it, and then we'll set the value either to 1 or 0 at that index. And we've got, of course, our little accessor for is solid. Then voxel compute is going to be largely the same thing. We're going to get rid of get voxel data and update voxel data. And then our voxel will now contain the functions within itself because it seems to be cleaner to me. So this is going to do the same thing. The only difference is our ID and our active value aren't in properties. They're actually functions, which kind of sucks, but that's a limitation within the compute shaders from what I've seen. Everything else works exactly the same though. We have an isSolid and an isTransparent function down toward the bottom of this just to help keep things a little cleaner. Now we're going to jump to our compute manager, and all we're doing here is changing the stride of our voxels and the noise buffer and modified noise buffer to accommodate for our integer and two unsigned integers that we're passing in. In doing this process, I have not gotten normals working correctly as of yet, so we're also going to come over to our chunk file and we're going to make sure normals are being recalculated every time, regardless of if we're sharing vertices or not. And then we're going to make our structures over in Structure Manager adhere to the new density field, which doesn't really matter. You can just set it to be completely filled and it'll do a rough approximation of it. However, if you set the density field like we're going to do for trees, it'll give it a much more rounded look, or whatever sign distance function you want to run. So our trees are going to actually be stored in an array of dictionaries because calculating the distance function for trees constantly is expensive. So we're just going to have a little for loop here running up to 6 because I want to have 6 different trees, so there's a little bit of variation in it. So all we're doing is we're making a new entry in the dictionary and then pretty much running our old tree code. As you can tell, the trunk is just being set to a completely full block, as I was saying you can do a minute ago. And then when we get down into the actual leaves where we're running that distance function, if the density is less than or equal to 0, it is going to be a leaf block. And then we're going to iterate over our little 4x4x4 density field within this position or within this voxel. And basically all we're going to do is check if the distance between the smaller density field's location and 0 is less than 0.125, which is half the size of a step in the density field. We'll go ahead and set the density as true, because that means we're within that range of the surface of a sphere. And then so long as our ID is 4 or our count is greater than 1, we'll go ahead and add that voxel into our dictionary. And then our new spawn tree function actually just becomes this, where we get our tree's random identity and we set the voxel at a position plus the tree's local position. Pretty straightforward there. Then we've got just a few small changes to make to the other generation. All we're going to do is set our density data and density data B to be the max value, so our density data will be reading as full. So we'll do this for our bush trunk, our bush leaves, and our rock. Now we're going to get into the less fun part. We're going to be heading into our height map compute, and what we'll be doing in here is changing the entire way this functions pretty much. So we're going to get rid of our sample height at point, and we're going to go with get density at point. This is going to be a pretty similar function, except we're also going to calculate our cave or cutout within this function. So you can see that right here. I have a bool hollow if the distance between our noise evaluation and our cave threshold is less than 0.125. That'll be true. If not, it'll be false, obviously. We cannot have caves below position of 1 just to make sure our chunk is rendering fully from the ground up. And then our density data that we're returning out here is either 1000 if it's in a hollow section, because it's going to work backwards. And basically that'll just tell it not to set anything as solid there. Otherwise it'll be our Y position minus our height value that was generated up here. And then we'll go down into our main function that is also going to get replaced entirely. So the top part of this is the same. Our voxel definition here that we want to make sure is just completely filled out has our voxel data being set to 0, density data to 0 unsigned, and B to 0 unsigned as well. We have our voxel ID placeholder. We select our noise layer that isn't actually doing any layering right now, and then we go ahead and calculate our corner density, or the basically starting point within the voxel for what our density is going to be. We check if we're a surface block, just like we were doing before. And then if our density that's returned by getDensity at point is less than or equal to 0, then our voxel is going to be either a surface voxel or a subsurface voxel. And then solid count is not actually being used anymore, so I'm just going to take that out. And then we'll iterate over our little density field just like before. Calculate the density at that point times 0.25 to get into the actual density field range itself. And then if our distance between density and 0 is less than 0.125, we'll set our voxel density to true at that location. If it still looks like we're going to have a solid voxel, or as it was determined up here, we'll go ahead and add it to our counter. And then here's our little foliage selector. If our Y position is equal to our rounded height, that's returned from getDensity at point, and the voxel ID that we're at doesn't equal 0, and it's not water, then we can go ahead and, or another special block, I suppose, with less than 240. We'll go ahead and reiterate with the same code we were using to generate foliage before. When it gets down to the check that's basically trying to verify we're not spawning a tree in the middle of, just the world, or on a 1 by 1 by 1 block on the side of a mountain, it'll just do the same thing as above. We'll get the density, output it to t height, because that's what was being used here before, as it's initialized right there. Check if that doesn't equal our rounded height, which is returned up here. And if it doesn't, then we can't spawn a tree. Otherwise, it'll continue running as it was doing before. If we get to the bottom and our foliage ID does not equal 0, which means we do want to actually place foliage here, we'll increment that counter and assign it to our special blocks buffer. And then we'll set our voxel ID down here at the bottom and set that voxel into our array. Down in clear array, we'll be just fixing our data initialization. Same thing as above, voxel data equals 0, density data equals unsigned 0, and same for B. I don't really have to specify unsigned, but the warnings are a little bit on the annoying side, so that at least keeps our warning counter down. Now we'll actually be going over to voxel values, and we'll be replacing our axis and cell centers by axis arrays with just this. So all we're really doing here is making it so we're only checking on the negative axes, as opposed to checking for each IDX or index around our cube, because if we were to continue doing that, if you take the top right front corner of a cube and move one space to the right, that's the top left front corner of the cube, and doing that axis switching will give you two different points at that corner, because it won't be checking the same block ID. So we want to make sure we're checking our block IDs uniformly across the entire grid, which means we're also wasting a considerable amount of computational power as we're doing this voxel compute, which I intend to fix in the following video after this one. Up here in shared verts, and our voxel compute file. Sorry, did not do a good transition there. We're going to add a float3 point, and then we're going to remove some functions down here just to clean up house a little bit. We're going to remove our unpack floats function because I see no reason we'll ever be using it here. Weird that this is here. And then we're going to remove our voxel is solid and voxel is transparent functions. We're going to remove get cell center for IDX. It's not used anymore. And then we're going to add a new function called approximate zero crossing. And this is pretty similar to what actual dual contouring will use. The only difference is as it steps through by whatever increment you're stepping through. Default in, for instance, tuck bones implementation of dual contouring would be 0.125, taking 8 steps across, but we only have a 4x4x4 density array, so gotta change it up a little bit. So what we do is we take our adjacent positions and we'll walk across on whatever axis is denoted by the difference between the two. So it'll be either x positive, y positive, or z positive, and we'll just step across in increments of 0.25. And that's all this is doing here. If it is our first run through. All right, we're gonna do this properly. The code I copied in does not have this functioning properly. So if it doesn't work, we'll just come in here and essentially remove this and basically make it a check that goes from positive into or negative. The intention is if you start on a solid part of the voxel, as you step across, you want to get the point where you go from solid to air. So before, all this was doing was checking if at our current step we're not hitting air. So as if we're going from air into a solid as opposed to solid into an air. So it'll be interesting to see what that does. Don't hold it against me if that doesn't work. If not, we can come back and fix that real quick. And then after all this mess, we're going to return our adjacent position with our access added to it times t, which is found up here by looking for, again, where we change from air to a solid or vice versa. And then our calculate contour function is also going to be replaced because this is frankly a mess. And this is our new calculate contour function. It's going to have a adjacent voxel B, and adjacent cell B, float threes. And then we're also going to have our world position based on our block chord and our vertex position. And then we're going to iterate over our 3 axes and our 4 adjacent cells at that axis. We'll set adjacent cell to be our world position plus the cell centers by axis at that axis and corner. And then our adjacent cell B to be adjacent cell plus our axis value. Assign our voxels according to those positions. And then if our voxels are not equal at those positions, we'll go ahead and add the approximate zero crossing at that between those cells to our position. Moving down, we're just going to return our normal as a float3 0 because I still haven't gotten normals to work, but it's been a while since I got a video out, so that's fine. You guys get low poly for right now. We'll fix normals at some point in time. Then we have a short check down here where our position, we're checking if any of our positions coordinate is less than our block position -1 or +1 so that we can keep our coordinate within a little bit of a range. It should help prevent outages or overages. And then moving on down a little bit here, It looks like I forgot to change this. So here, when we want to get our block ID, it's just going to be block.getID, which seems a little bit cleaner to me. And then our 8 vertices that we're checking per position, we're just going to go ahead and pre-calculate up here, because if you're doing the low poly look or non-shared vertices, you're recalculating those positions so many times it's not even funny. So might as well pre-calculate it. So we're just iterating over our 8 points. We're calculating the contour at those points and adding it to our adding our chunk position to that, and then setting the vertice at that index to be our new position. And we're setting it as set to false, so that when we do the shared vertices running of it, it'll let us actually assign the index to it properly and all that good stuff. We'll move down to our face checks to make sure we're not trying to find a crossing between 2 transparent blocks or a solid block and a non-transparent block. And we also have a new check in here, if you noticed, where we're just trying to make sure that we're not checking below the ground, because it'll return empty, obviously, and that's not good for us. We don't really care to draw the bottom face of the 0 Y height voxel. And then we'll move down just a little bit here. We're going to remove our for loop where we set face vertices, and also remove that array from up here. And we'll replace our vertex buffer addition with our vertice from our verts array, accessing it via the voxel tries mapped, which gives you the IDX or the index of our current vertex via the face and the current voxel vertice we're iterating over. And then going down to our shared vertices function, I'm going to be replacing the entirety of it here. We're just going to do this. So we'll still get our index via that voxel tries mapped map. And then if our vertice has not been set yet, we'll go ahead and add that we'll add that vertice to, would it be vertex? We'll go ahead and add that to our vertex array, or we'll go ahead and increment our counter, set our index for that vertice as our counter, and then our vertex buffer will get the vertice normal and our color placed at that vert count that we just got. Then we'll increment our triangle count according to the index that we have here. And that should do it. Let's see what kind of mess our zero crossing makes right now, because that was not what I've been testing with recently. So far, so good. I wonder if it makes any difference. Yeah, it's weird. Let's go take a look. I mean, it looks a little bit more ridgy. Is there any artifacts? Yes, there. No, that's a watertight mesh. Our trees are nice and shiny, looking about right. We do have some floating cells over here. So I don't see anything inherently wrong with this. It still looks to be a pretty smooth terrain. We'll go check out our mountain, because this is where everything is going to get messy, if it is going to be messy. No, I mean, our mountain looks pretty fine too. Alright, so let's just go ahead and pause here. And then we're going to go back in. We're going to go up to our approximate zero crossing function. And we're just going to comment this section out and see if we can play spot the difference. Go ahead and run this again. Well, we still have our little floating thing here. The terrain still appears to be pretty smooth. Let's go see if we can find that weird vertex I saw. Yep, it's still there. All right, well, I'm not honestly totally sure that there's any difference between that function running the way it was written to run and the way I typoed it. So let me know down in the comments below if you can play spot the difference there, and let me know which one looks better if you see a difference at all. Might be the mountain that's doing it. Let me double check one thing real quick. All right, let it wait and get back to our mountain. I think it helps clean up some of the pock marks on the mountain, but I'm not 100% sure. So yeah, let me know down in the comments below if you can even spot a difference and if it really matters, because I'm not confident it does. But that's all I have for you guys today. Thank you for waiting patiently while I figured out how to make this fairly smooth terrain work without actually sampling properly, because why would I do things the proper way when I can make it much closer to Minecraft standards? And as always, if you like what I do and you like the content I'm trying to make here, you can go find my Patreon in the description of this video. You can also find a link to my Discord channel where you guys can come hang out, ask questions, show off whatever projects you're working on right now. Next time, hopefully we'll be working on getting some more speed out of this, because that initial generation takes a minute. So look forward to that, and I will see you guys in the next video.